Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous video, we explained the principle of operation of autotransformers and their economic advantages. Today, we move from construction to control. We will see how voltage regulation is implemented in autotransformers, what schemes are applied, where the regulating points are located, and how this affects the operation of the device. We will also examine the main operating modes of an autotransformer and the differences between transformer and autotransformer connections. Why voltage regulation is needed. Power networks operate under variable loads. Demand fluctuations cause voltage variations in the line. To keep stable voltage at the output, transformers must compensate for sags and peaks. Regulation is performed by switching taps in the regulating winding. This makes it possible to keep voltage within the permissible limits, improve supply reliability, and reduce technical losses. Voltage regulation scheme. On the high voltage side, options without reversal, with reversal, or using an auxiliary transformer. Advantages: regulation without breaking magnetic coupling, protection of the high voltage winding, possibility of use in medium and high voltage class transformers. Disadvantages: high requirements for switching equipment and insulation, more complex circuit and tank design. On the low voltage side, options are similar: without reversal, with reversal, with auxiliary transformer. Advantages: simpler construction, low voltage switching equipment cheaper and more accessible. The tap changer can be placed outside the tank. Disadvantages: higher switching currents, reduced mechanical strength of the regulating winding in the neutral point. The regulating winding and tap changer are located at the neutral point. Advantages: minimal operating voltage on the tap changer, simple insulation and switching. Overall switching voltage can be reduced to 15 to 20% of the high voltage. Disadvantages: requires accurate calculation of current balance, difficulties when modeling overvoltages. Rated regulating power. Depending on the scheme, part of the regulating winding participates in carrying the full load. This affects the rated technological power of the transformer. It is expressed as a rated regulating power equals rated power without regulation plus 1/2 multiplied by the sum of the main power and the additional power. With regulation in the neutral, the rated power increases more sharply with the growth of the transformation ratio. When the transformation ratio is greater than 1.6, the rated power of neutral regulation schemes can exceed the rated power of a conventional scheme by 1.5 to 2 times. Examples of operating modes of autotransformers. High voltage to medium voltage or medium voltage to high voltage, main autotransformer mode. Most of the energy is transmitted directly, the rest is transformed. Short-circuit losses are 60 to 70% of maximum. This is the typical mode when transferring energy between two high-voltage networks, high voltage to low voltage or low voltage to high voltage, pure transformer mode. Energy passes through the tertiary winding. Short-circuit losses are about 50%, used for supplying distribution networks from the main input, medium voltage to low voltage or low voltage to medium voltage. Characterized by small currents and low power. A large share of winding losses makes it inefficient for long-term operation. Combined mode, for example, simultaneous operation on high to medium and high to low voltage. Danger: overload of the series winding requires limitation of current in the common winding section. Choice of regulation scheme. Depends on voltage class, operating conditions, heat, frost, gas content, maintenance, accessibility, size, and weight limitations. Comparative analysis. On the high voltage side for large networks with a high degree of standardization, on the low voltage side for distribution substations and backup transformers, in the neutral for extra high voltage systems from 500 to 1150 kilovolts. Practical example, suppose we design an autotransformer rated 220 to 110 kilovolts with regulation of plus or minus 10%. Comparison of schemes, high voltage side regulation, 220 kilovolt insulation, compact but costly insulation. Low voltage side regulation, cheaper switching but higher thermal load. Neutral regulation, minimal voltage but complicated insulation choice and labor-intensive tap changer design. According to calculations, neutral regulation gives up to 8% weight savings and 4 to 5% cost reduction when the benefit factor is less than 0.6. Practical analogy. Imagine an autotransformer as a multi-level water supply system. Pressure is like voltage and the valves are the regulation schemes. If the valve is at the base in the neutral point, it is easy to operate, but hard to balance evenly. If it is at the top, operation is more expensive but more reliable. If it is in the middle, it is universal but harder to balance. Practice task. Calculate which regulation scheme will give minimal rated power at a transformation ratio of 0.7 and a given power of 160 megavolt amperes. Plot the dependence of rated power on the transformation ratio for neutral regulation. Compare rated power at transformation ratios of 1.2 and 0.9 for all three schemes. Today we learned what regulation schemes are applied in autotransformers, how the choice of scheme affects weight, cost, overload, and stability, and what operating modes are typical for autotransformers and how they affect losses. In the next video, we will move on to the topic of short circuits and overvoltages. We will see how autotransformers behave in emergency conditions and how to ensure reliable protection. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.